Welcome back. This topic is Learning Module 8, which is File Input Output. We'll be learning about basic file I/O in C, reading and writing to files, the difference between text versus binary files, as well as learn a little bit about handling different file formats. Admittedly, the topic I think is a little dry, but it'll be a good opportunity for us to sort of bolster our existing C skill set. Part of the motivation for File I/O is, in some sense, it's been pretty clear that the way we've been entering data so far, using RAN to generate a whole bunch of data, or just a whole bunch of scanf requests over and over again, or the example I showed but we didn't actually run of using argv from the command line, it's pretty limiting. There's a limit to how much things you could type in or randomly generate and have meaningful data and so forth. The standard C library gives us a pretty simple mechanism for reading and writing files, reading and writing to files by capturing data as either binary or text. File access in C is very similar to how you would do it through your conventional operating system. You can access files via a relative path, like just myfile.txt if it's in the same directory, or via some absolute path, either a Windows style path or a Unix type path that we'll be using in our Replit environment. Underneath the hood, we've actually been using two files all semester. These are defined in the standard library for standard in, for reading from the command prompt, or standard out for writing back to the command prompt. And we're going to see that a lot as we're covering these functions. For a large number of them, they're actually just a special or more, general case of the same functions we've already been using for console I/O. So there's a scanf that we've been using. It's actually just a special case of file scanf or fscanf. We've been using printf all semester. fprintf is printing to a file versus just printing to standard out by default. So for a lot of the syntax, we already know it. We just need to get a little bit more exposure to how we're dealing with files on a practical basis in terms of reading and writing and the general file model. C uses what's referred to as the I/O stream model. So a file is just a stream or a sequence of bytes. Consequently, you don't really have to read an entire file or have a single variable that represents all the possible data in a file. The data type that the standard C library uses is a pointer. It's a file star pointer that can actually also keep track of where you are currently in the file in terms of the current position. You can read or you can write to that position, or you can actually move the position where you are in the file via various function calls. So if you had some file, myfile.txt, you can visualize that as just a stream of bytes as well as a pointer to the position you're currently at. It's not so different from the old kind of VHS tape analogy where it's this stream of data and you can kind of physically rewind it or fast forward it through your video. It is kind of analogous and invented in the era where we had magnetic tape for our storage and file systems. The same model still works really well for modern systems and modern files. So we have this special data type defined specifically for accessing files, which we use via pointer. We have not covered pointers yet, but we've covered enough of them that I think you can use this syntax: file star myfile or input file. So we have a pointer to a variable of type file. Next, there's a call to a function called fopen, where we pass two things: name of the file. In this case, it's a relative path. So relative to the directory I'm currently executing my code in, there should be a file named joe_file.txt. The other string is the mode of operation for which we are reading that file. In this case, we're going to pass it just the string with just a single character R. That means we're going to open this file in read mode. As very good practice, we should be checking if that call to fopen failed. Did that file not actually exist? We check so by checking whether or not the pointer is returned as a null pointer or not. And if so, our program really shouldn't continue. We should not try to read from a file that doesn't actually exist. Let me just show pretty briefly what this looks like in practice. So this is learning module code 801. I have a very simple file called joefile.txt, and syntactically we can do exactly what was on that slide. We declare our file pointer, we can call it myfile. We set the result of myfile as the result of the function fopen. In this case, we're going to want to read to that file. We should always, as good practice, check, was that read successful? If it wasn't, we'll say problem opening file. We should get out of the code. We should either leave the function, we can return some error message. Otherwise, we've successfully open the file. And that's sufficient for our purposes now. We've successfully opened the file. That can at least run. There is a file. We get successfully open file. If I change it to Joe file 2, we get problem opening file. We'll come back to this example. From a computer systems or computer architecture perspective, a file usually just implies that there's a block of information arranged just according to some preset format and stored in some type of non-volatile storage, some sort of storage that keeps its information even when you power off your computer. But from the programmer's perspective, and from our perspective here in this class, it's just another region of memory that we can access. So files are just going to be laid out as a sequence of bytes, just like our memory is. And our programming challenge is a little bit different, that we have to understand in looking at a file, how should we interpret those bytes of data as particular data types we may have. So while architecturally what's happening with a file type is a little bit more complicated than with a regular block of memory, from the programmer's perspective, it's really just a matter of opening, closing, reading from files, and then the programmer's challenge is not those functions themselves, but how do we apply those functions to gain some meaning to the data, to modify data, to do something interesting with the data that is then stored in files. So as I mentioned, there's that second input to fopen, which allows us to specify the mode in which we're opening the file. So fopen joe.text or text.doc, in this case, ASCII reader reading it as text. There's several other options, and you will find some, I would say, older or non-standard documentation that says there's a B flag for open as binary file. It doesn't quite do anything that interesting. So really the read, write, and append are the three modes that are the most commonly used and the most interesting. R for read, W for writing a file, append that allows it to write to the end of the file. And this table is pretty good to have handy when you're thinking about working with files. So for example, if we open a file in write mode with W, if the file didn't already exist, we create a new file. If the file already exists, we overwrite, we blow away that file. That may be what you want, but that may be exactly what you don't want. The append mode, if a file already exists, it doesn't destroy the contents, it adds to the content. That may in fact be what you want. And then there is a mode to open for read and write of a file simultaneously. That's not as common as just doing read or write as kind of separate operations. That's our call to fopen when we want to open a file. The $64,000 question is, can we guess how are we going to close a file? And if the function is called fopen to open the file, I think it's a reasonable guess that our function is going to be called fclose to close a file, and that is absolutely the case. That's not going to do anything interesting in this code other than just allow that file to be opened by some other application or some other part of an application. So now that we can open a file, the question is, what can we do with it? We can write to it if it's open in write mode. The same exact syntax we use for printf will apply now to fprintf, file printf. Input, as the first input now is not that string, it's just the name of that file pointer variable. It'll act exactly as printf, except in printing to our standard output. We're printing to that file, we're updating the contents of the file. Likewise, for our scanf, getS, other functions we've been using all semester, additional things that are possible using the file in our I/O libraries, we actually have functions that can check, have we gotten to the end of the file already? We have functions that can actually manipulate that pointer in terms of where you are position-wise inside that file. That can sometimes be quite useful to know, hey, are we done reading the file? Can we actually start over? Can we seek to a specific location in the file? We can get pretty far using just the file subset of the same set of functions that we've already been using all semester. So the example I have here is called file write. We're not going to actually code it here, we're just going to kind of explore it. We have the reference for the file IO functions, and actually you may have already noticed that when we've been looking up the reference, for example, to scanf, it's the same exact reference as for fscanf. There's also string scanf that you may have already been using, but we didn't explicitly need to. They're the same exact function with slightly different inputs that act exactly the same way. So for our example called file write here, we can kind of just follow along with the syntax. We declare our file to a file called new file, open for write mode. I've already run this, that's why that file already exists, but we can just delete it and we can still run this code. Open new file in write mode. If we had an error for whatever reason, we should get out of here. It's not going to go well if we're not already having a valid file. We can use our fprintf just like we were doing our regular printfs in the past. Print text, print some numeric value, etc. When we're done, we should close up that file. After we've closed that file, we can then open it again for reading. So if we had attempted to do this fopen while we hadn't previously closed it, it in fact was going to give us an error. So we close it first and we can then reopen it. And there's all sorts of different ways we can process the text in our file. This is a pretty common approach in which we have in our while loop, we're constantly checking, have we gotten to the end of our file yet? And while we do so, we actually call our fgetS, which is the same exact function we've been doing in the past. This is a bug, right? If our line buff is defined as size 256, we should only be reading 256 bytes at a time. We run this, we've printed to a file, we then read off exactly what we are reading from a file. Because that fgetS returns our new lines, we don't really need to add a new line to that. Printing to a file, it's exactly the same as printing to our output, and there's my favorite number. And that actual contents is now in the file because of those fprintf calls that we had there. That leads me to an in-class exercise I would like us to try together. It is something I think we can handle because we've been sorting data now all semester long in a couple of different ways. But now we're going to be sorting data that isn't being generated via RAND, isn't being typed in by a user, but it's data that just exists in a file. That adds a small wrinkle, although the main computation is going to roughly be the same. We do have to have some mechanism for knowing, am I done with the file? Did I grab all the values that I actually need to grab? So there's some assumptions we have to make. In this case, let's assume for the purposes of static memory allocation that there's going to be 100 or fewer elements in the file, but we don't necessarily know how many in advance. We already know how to do the sort. The question really becomes, how does the rest of the program look? So this is example 803 file sort. I also have example 504, which was our bubble sort or our array sort example here. We're going to be able to adapt that. The challenge is, how do we get a file version of this same exact code? So I already entered in a random.dat, which was the same exact example. There's a little bit of a chicken and egg problem here. How do I generate the random.dat? Well, I probably have to write a program that generates random numbers and prints them to a file. Assume we already have that file generated offline and via some other mechanism. Our job now is to generate a sorted.dat that actually has those same entries in sorted order here. Let's think about the rest of what we have to do, and then we're going to try to integrate with what we already would have for the sorting part. Well, we have our file pointer, and this program is going to be working with two different files. So we have our in file and out file. We could call it random file and sorted file. It's just the name of a variable, right? We're going to want to open that random.dat in read mode. And we're going to have our output file. So calling it out file is a common design. Sorted.dat, now this one's going to be in write mode. And I'll leave a comment here for brevity that we should really check for error on file open. But who has time for that? I know random.dat exists right now, and I know I can open sorted.dat, but we should do that if equals null check and exiting out and all those kind of things. We need to actually then read those input values, and it can be exactly like how we read in the 5 values when we had just those 5 variables by hand, right? We can do our, not scanf, but we can do our fscanf of our in file, which that's the new input to this, %d, and there was a comma and a space, and we have to actually store that result as a val. So let's declare our value. Then we have our fscanf to store that result as a value. That should give us a single value. Let's confirm that this actually worked. Read in %d. This should print out whatever that first value was in that file. Read in 15. It did create that sorted.dat, but we didn't do anything with it, so that file should be empty, and it is. Read in 15, that's pretty promising. Now the challenge here again is we know there's 100 or fewer elements inside that file. We don't actually know exactly how many there are. That is a little bit challenging. One nice feature of the scanf and fscanf functions, it actually returns whether it successfully was able to read a value or how many things it was able to match in the input string. And we can actually use that. We could say, let's continue to fscanf. We could have used the end of file primitive, but we can do this method as well. Let's continue with fscanf while we're still reading valid stuff. While it is still returning 1, let's keep doing fscanf. That's a bit of an issue with regards to val, but we can't keep reusing it eventually. But for now, that's fine. Hey, read in it. Let's just print out all the values that are in that file. 15.4, -6. I hope that's correct. Yeah, that's the value that was in the file. We got the last 77. We can certainly close that file now that we got to that point. We've read the entire file. We've read it all to one single variable. We know we want to get that into an array. And so now we're back to what we have for our older array sort code. And it's going to be, I think, pretty cool how we're going to be able to adapt this code for our new purpose of sorting the file. We need to declare the array. We don't need to declare it globally, but we did in the previous example. We know now in this case, it's an array of size 100 for our maximum case, but we actually need to keep track of how many elements there actually are in the array. One way to do that is every time we've successfully read something, do that kind of count plus plus, right? For now, we probably don't want to print it out anymore, but we actually want to take the value that we've read and update our array at that index, starting at 0, incrementing upwards. We could add some checks. If we got to greater than 100, we're in trouble, but that's part of the spec that it should be 100 or fewer. Some people would say, combine these 2 lines of code into one, like we talked about with postfix increment. Let's not be too clever. So it's 2 separate lines of code. We're not paying for lines of code here. We're fine. Update our array count and then do a count plus plus. And then the cool thing, I think at this point, we should have an array with a known number of elements in it in unsorted order. And the rest of the code should be pretty close to copy paste. We don't need a random seed. We don't need to generate random. We don't need to print out before sorting. But starting where it says textbook bubble sort, we should essentially be able to do that in our code. It's not going to compile. You always have to be careful when just copy pasting things in. Why is it complaining? It's complaining about temp. Okay, temp must have been defined elsewhere in that other code. Fine, we have temp local to that loop. We should be okay. We're sorting array. The other big gotcha would be, this is sorting array always of length 100. We are now sorting array of length count, which is a runtime variable. But otherwise, that code should just work. And likewise, for our printing, we have our printf %d comma space of array of I. The only change we have to make now, fprintf to the out file. And we should close our out file at the end, which is corresponding to sorted.dat. And in fact, this code doesn't print anything at all, right? Because it's all printing to file. There's random.dat, and there's our sorted.dat. It added an extra comma. We know how to get rid of that, but it doesn't matter for this example. And we're just using our function open, fprintf, fscanf calls to do essentially the same exact logic, and now doing it in files. This data is available offline. It's available after the code has actually been executed. That adds a lot more power to the type of programs we're actually able to run here. I also want to talk a little bit about the scanf format strings. I always talked about how there is a reference for how to do that in terms of looking up what the various flags are indicating for scanf and printf. We did a little bit of work with the different precision values. It's kind of just a reminder that you can always Google up this information, and if you need something to be printed a specific way, there's usually an answer for it. So it's not something you should try to reverse engineer from base principles or anything like that. We should be able to find the answer for how should one reverse, or how should one print out a string in a very particular format. When it comes to file I/O, that sometimes becomes more important because we may need a file to look a very particular way to get the result that we want back out. This slide just includes some examples. Our main I/O tutorial website that we've been opening up here has all the default examples we need, and you just Google or Bing or whatever the results. When you actually do need to do something very specific, you can generally find the results as the first hit on your search. An important thing I want to then touch upon as kind of our final topic in this video is, haven't we discussed and decided that everything at the end of the day is just ones and zeros? Everything is binary. So what was this discussion about text versus binary files? everything is a binary file, right? In a sense, right? Everything is stored as ones or zeros. That is technically true, so I say, well, yes, but actually, no. There is a difference in storing data in this text format versus storing data in this binary format. First off, we'll see there's a difference in terms of how much storage it requires. If I want to store an integer as text data, I have to convert it to the equivalent ASCII amount of characters for that text data. Each of those characters is 8 bits. It's possible my int itself is only 8 bits. There's an extra overhead of storing. The files will themselves be quite a bit larger in human readable text mode versus just binary blob mode. The second aspect of that is that there's actually different functions that allow us to write blocks of data in binary form versus in text form. We haven't learned these functions yet, but here's the reference or the declaration for those two functions. There's fread, sometimes just called Fred. There's fwrite, that's for the binary read and the binary write. The syntax is a little bit less intuitive than our trusty fprintf, fscanf, but it's taking the equivalent of an array of data. You're telling the function call how many bytes you're writing. So it's a little bit closer to our memcopy and string copy calls we've already done. And then it's doing that all as one block of data at one given time. This example is the binary file example. And I've already written it for you, but we can look at this. So for an example where we have, again, an array, in this case, again, of size 100, we initialize it with some random values. We then have our two different files we're going to want to write to test the results. One is a text file, that's just the name of the file, mydata.dat. .dat doesn't mean anything, but historically, if you had like a text data file, you might be called .dat. When we open that file and want to write to it as text mode, fprintf is a perfectly valid choice for that. Whether we separate the data by commas or spaces or new lines is this case, it's roughly the same number of bytes anyway. We open that file, we loop through the array, we print to that file. Now we open up a separate file that we label as binary file. We call this data.bin, but something, at least in the Linux philosophy of the world, those file extensions are just labels. They don't mean anything. Calling something .bin doesn't make it any different than calling something .text or .dat. But for human readable names of files, that can be somewhat useful. Okay, that's going to correspond to a binary file. And I mentioned you will see some older documentation that'll mention if you want to write something as binary, you have to open it up as WB. That's not true. This W will work perfectly well. Then it just so turns out that the actual format for writing to that file, the function we can use, that fwrite, is quite a bit different. Here we can pass, as opposed to looping through an array, printing them out one by one, like we've been printing out all semester, we have a single function that's essentially like a memcopy from array to our file called fwrite. We pass it the array, effectively the pointer of the array. It doesn't ask for a number of bytes for whatever historical reason. Instead, it asks, what is the size of each element in the array? So that's 4, or size of int. And how many elements are there in the array? That's num_vals. For whatever historical reasons, that's a slightly different interface than what memcopy had, but it's doing something extremely similar. We run this code, it doesn't actually print anything out. We can see the human readable version of our mydata.dat, and this mydata.bin is in fact encoding the same exact information, just not in a human readable format, right? We're encoding the ones and zeros of the actual integers themselves into that file. So it's not going to be human readable anymore. Our replit editor is trying to figure out what exactly is happening in this file. There may be a binary editor installed on the system, and there may not be, where we can actually, well, I have to install it in our system, but that actually enables to look at the actual ones and zeros or the hex equivalent, and you can see that it doesn't correspond to anything in ASCII. But if you want to know what's the value of byte 2, you can see it here, and that's fine. The other thing that's different, though, is as we've generated our 100 text data integers in a file versus our 100 binary values in a file, is the data file is going to be quite a bit bigger by a roughly constant ratio if we're talking about integers, but that ratio could grow. Other interesting thing is, of course, just like before, this code doesn't really change as I go from 1,000 or 100 to 100,000. It's going to take a little bit longer to run, but it's still pretty darn fast. Printing to a file tends to be a little faster than printing to I/O. We have our massive this file, .dat. We can compare the size of those two files and see that, we can actually accurately predict to the byte how big our binary file is going to be. It's 100,000 integers. Each of them are 4 bytes wide. That file is exactly 400,000 bytes long for that exact reason. Whereas the ASCII file, it really depends on the integers, right? In this case, some of the integers are bigger than others. If we were to do a mod operator instead and say, hey, every integer is going to be 1 or 0, that's what that modded operator does for us, then the size of those files becomes interesting again, right? It turns out now in this case, the binary one is still 400,000 bytes because every integer is encoded as a 32-bit value or 4-byte value. But our actual characters is quite fewer because it's just a 1 or a 0. So it's 1 new line, 0 new line, 1 new line. Each one is encoded just as 2 bytes. It's actually smaller in that case. But in the more general case, I think it's safe to assume and operate off the principle that your binary file, while not a compressed format, is going to require fewer bits to encode the same information as your text file would in general. Let's leave things there for today with regards to understanding at the basic level text file I/O. We have a couple other examples I'm going to want to walk through in terms of understanding a couple different file formats and just some more examples of coding with file I/O. Again, it's really not anything that new because it's the same class of functions we're using. The binary functions are new, but they're kind of similar to the ones we've already been using. It's still just another opportunity to have kind of deeper problems to solve because now instead of worrying about typing in a whole bunch of input text or randomly generating input values, both of which are kind of limiting in terms of getting good input data, now we can generate a dictionary or download a dictionary and use that as our entire input set. And some of the programming practice problems, and as well as the problem we'll look at in the next video, allow us to do that. Leave things right there for right now, and we'll jump on the other side and do some more practice together.